Next, we'll look into a bit of third law of thermodynamics, because entropy is related to, or entropy is the absolute entropy is defined by a third law of entropy, the third law of thermodynamics. So the definition of third law of thermodynamics in terms of entropy is a crystal of pure substance will have zero entropy at zero absolute temperature, or 0 Kelvin. Okay, so if we have a pure crystal, its entropy will be 0 at 0 Kelvin. That's what the zeroth law of thermodynamics on the basis of entropy says. So in statistical thermodynamics, the definition for entropy for statistical thermodynamics or a microscopic system is defined as S is equal to R by NA log omega, natural log of omega. So R is the characteristic gas constant, and Na is the Avogadro number, omega is the number of microstates. Okay, these things we already know what they are. Omega, that is the new parameter, that is the number of microstates. So what we can say is, as temperature, we all know that as temperature decreases, from the definition of entropy we have C is equal to, or ds is equal to delta Q by T. So as temperature, and we have said that Q is a function of temperature gradient. We have seen that Q is also a function of temperature gradient. So as temperature decreases, we can observe in nature that as temperature decreases, if we have a gas, if we put or pull sufficient amount of heat from it and reduce its temperature at significant pressures, it may liquefy, and after significant liquefaction, if we pull more heat from it by imposing more constraints on it, it will turn to solid. Or in a classical case, we can take the example of a water. In a classical case, we can take the example of water. Water at standard temperature and pressure boils at 100 degrees Celsius, or it liquefies at 100 degrees Celsius. It liquefies at 100 degrees Celsius, and if we cool it significantly at 0 degrees Celsius at standard temperature and pressure, it will freeze. Okay, so as we cool things down or pull heat from it, things or pure substances, pure or impure, we look into pure substances more, or we'll be interested in pure substances more, because pure substances will have more order into it, or as it'll be more ordered. Okay. So if we consider a liquid is just like molecules that are running around in random fashion. We can't put up a point and pick a point in the liquid and say, I have found an atom in it. The atom of that particular atom in it. In case of a solid, the probability of finding an atom at a particular location is much more than finding an atom of a liquid at that particular position. So what we can say is, as we cool things down, the probability of finding an atom at a particular location, or a fixed location, that is in the lattice structure. Suppose I will just draw a simple cubic structure. So this is a simple cubic structure. If I define that lattice structure in a lattice structure, this is what it is supposed to occupy. The atoms are supposed to occupy. At 0 Kelvin, for pure substance, we assume that the atoms will occupy these locations. Okay, so they only have one, or their energy. Every system in this universe will try to have a lowest energy. Okay, would like to be in its lowest energy form or lowest energy state. So at 0 Kelvin, the system that is the crystal or the lattice itself, would like to be at its lowest energy form at 0 Kelvin. So this, we assume that it only has one microstate. Okay, this particular lattice is its only microstate. So as we increase the temperature, the molecules will tend to vibrate more. It will have much more energy, and it will be much more free to move about. So the probability at 0 Kelvin, the probability of finding, we assume that at 0 Kelvin, the probability of finding a particular atom at a particular location is 1. P, let's say A, is equal to 1. But as we increase the temperature, the probability of finding an atom at a particular location is always less than 1. Okay, as we increase the temperature significantly, it will drop. The probability of finding the atom at that particular location is going to drop. So this is what we call as the microstates. So anyway, the atom cannot occupy any random location. It has to occupy particular locations. Okay, depending upon its energy state. These locations are called as its microstates. So as we increase in temperature, the microstates will go up, and hence, by definition, as the microstates go up, the entropy of the system will go up. Okay, so this is what third law of thermodynamics says. That is, for a crystal of pure substance at 0 Kelvin, it will have 0 entropy. Okay, so this is where we get the idea of disorder. That is, as temperature increases, the entropy, as entropy goes up, that is the number of microstates goes up, the system will have like a disordered appearance, or the number of microstates are so high that the system itself is in disorder.